5.5 u substitution. The way to think about u substitution, it's a technique of integration, and it's really the reverse chain rule. It's trying to undo a chain rule for a derivative and work backwards. Okay? So just like we had reverse power rule and things like that, so too this particular rule for derivatives has an inversion process, a method for antiderivatives for integrals. So let's just take, for example, here something that looks very simple but could be quite challenging without this rule. Let's say you had the integral of the square root of 2x plus 1 dx. So to find an antiderivative, because that's not so clear, it's hard to just look at this and think, what did I differentiate, right? What function did I take the derivative of to get to this integrand? Now, the reason it's called u substitution is because we're going to make a substitution. We're going to let some function u, right, be some part of this thing. Now, the part we select is important, and through doing a lot of problems, you get more intuition as to what to select that u should be. Right now, a good rule of thumb is wherever you see composition, you should let the inner function be u, at least as a first try, right? This is a method that you may have to apply a few trials to before you get the correct antiderivative from it, before the method is successful. In this particular case, the only composition that I really see here is that 2x plus 1 has been put inside the square root function. So since I'm viewing this as an inner function, I should probably let u be this inner function, and we will probably have success. Not always, but probably. So that's my first move, is just declare this variable u, which is why it's called u substitution, because this is the quintessential variable used. U equals some part of what's going on in here, and I'm going to choose it to be the inner function. If I see any type of composition going on, I'm going to choose it to be the inner function, at least as a first guess, for what u should be. So once I have that, I'm going to take the derivative with respect to x. So du dx equals 2, because it's a linear function. That immediately implies, moving this differential over here, we'll have the du equals 2 dx. Right? So these are the two parts I want. I want to declare u to be some part of this function, the integrand, usually the inner function, right, of a composition. And then I immediately take the derivative and I move the differential dx to the other side. So I have du equals 2 dx. And now what I try to do is I try to fill in all the pieces of this integral that were in x, and I try to fill them in with the variables u. So du needs to replace dx somehow, and u needs to replace all the x expressions in here. So clearly if I just substitute in u for 2x plus 1, that works directly, and all the x's are gone from the integrand. But I still have the dx here I need to replace with du. But dx is not exactly du. Double dx is du. So what I should do then is move this 2 over here to the side. So this implies that dx will be a half du. Okay? In other words, it doesn't matter much for the problem in terms of mechanics, but just if you think about it, it means that an infinitesimally small change in x is equal to 1/2 times a very small change in the variable u. That's how they're related. Change in x is a half change in u, as long as u is equal to 2x plus 1. So now what I'm going to do is I'm going to replace all the pieces in here so I get a new integral in u instead of in x. Okay? So we will have integral the root of u, and dx we said is 1/2 du. Okay? So 1/2 du. Now this 1/2 is a constant. Everything's being multiplied together here, right? This really is a product here. Root u times 1/2 times du. Even up here, this is really a times dx. You don't really think about it that way. We just think about the integral symbol going with this dx symbol all as one operation. But in reality, this is a product here. So this is also a product. So this 1/2 can move to the outside because of the constant multiple rule for antiderivatives for indefinite integrals. So this is the same as 1/2 integral root u du. So now we just need to take the antiderivative of the root of u. But the root of u is the same as u to the 1/2 power. And now we can do an inverse or reverse power rule on it, however you want to talk about it. So that should be the same as 1/2. The power goes up to 3/2, and then I multiply by the reciprocal. So 2/3 u to the 3/2, and then plus c, because this is an indefinite integral for my example. All right, so that's a product. So the 2's cancel here. We get 1/3 u to the 3/2 plus c, but u is really 2x plus 1. And my original integral is in x, so I want my answer to be in x. I don't want to leave it like this. I want to resubstitute now 2x plus 1 for u. So 1/3 2x plus 1 to the 3/2 plus c is our answer for this particular example. And what's a good idea to do at first when you're working these problems, after you feel like you have some success with getting the answer, is to differentiate this very quickly in your mind and make sure that if you were to take the derivative of this expression, you would get back to the original integrand. Okay? So I'll just do it very quickly. Again, just mentally. You don't need to work out the whole thing. 3/2 would come down. 3/2 would cancel 1/3, giving us 1/2. Right? So I'd have 1/2 2x plus 1, and this would lower by 1 to 1/2. So I would have 1/2 2x plus 1 to the 1/2 times the derivative of the inside, which would be a 2. So I have 1/2 2x plus 1 to the 1/2 times 2. The 2 and the 1/2 cancel, and the 1/2 power is really a root. So I'd have the root of 2x plus 1. That is my integrand. I'm now confident that this is the correct answer.